Hey there, class. Here we're going to look at an example. So let's take a look through the example here. It says a roller coaster on top of a 30-meter hill travels at 2.5 meters per second. When it reaches the bottom of the hill, it is traveling at 20 meters per second. Is mechanical energy conserved on this roller coaster? If not, how much energy is lost to non-conservative forces? So I'm going to start off with showing that we understand what's going on here. And specifically, I'm going to do that by drawing a picture. So let's take a look. We know that this starts at the top of a hill. It's going to go down here, down to the ground level, and I'm going to call that my zero level. That's a convenient place here on our problem. So when I look at the top of the motion, the roller coaster starts there at the top of the hill. So it will clearly have potential energy because it is above the ground. So I know it's going to have potential energy. Next thing I notice is it's moving. That means it's going to have kinetic energy. So my total energy to start is due to both parts of the energy. The total energy is made up of the mechanical gravitational potential energy and the kinetic energy. Now let's look at the bottom part of what's going on down here. So I'm going to zoom in on that. So it goes down the hill. At the bottom of the hill, we know that it's traveling at 20 meters per second. So because it's moving, we know that it's going to have kinetic energy. We also notice that it's now at the zero level. The height is zero. So therefore, potential energy will be zero at this point. So when we total up our energy, we'll notice that the total energy is at the end here is just the kinetic energy because the potential energy is zero. So here's how my strategy is going to look. I want to take and look at how much energy we have to start and how much energy we have at the end. And again, it's not individual energies, it's total energies. So I'm basically going to set the energies equal. Here at the beginning energy has to equal the final energy. The beginning energy was kinetic plus potential. My final energy was kinetic only because it has no height. I noticed that when I substitute the expressions in for potential energy, for kinetic energy, and kinetic energy final, I notice here that every one of these terms actually has an m in it, which means the mass is going to cancel. So what I'm going to then do is, after it's been canceled, I can actually go ahead and substitute my numbers in. And there's I've substituted my numbers in. And what I notice here is that these two things do not equal. This right over here would indicate our beginning, and this would indicate our ending. I notice at the ending there is less than at the beginning. So this would indicate to me that mechanical energy is not conserved. So if we go back and refresh our memory, I think what we had to do here, if not, how much energy is lost to non-conservative forces? So let's take a look at the second part of this. We know that mechanical energy was not conserved. So what we want to figure in is how much was lost. So in my equation, I'm going to just alter it just a tiny little bit here. Notice that I still have my mechanical energy here and here, but I'm also going to factor in the amount of energy lost. In other words, it's energy done by things doing work that are external, or again, this is what we might sometimes call as an open system. It is open to external forces. So basically, the only change I have here is that I'm going to include this extra term of the work being done. So you're going to see a very similar kind of pattern going on here. I'm going to actually solve it here for a slightly different variable. I'm going to solve it for here. And what you'll notice here is that in this case, the mass does not cancel out. So here's what I'm going to do. I'm going to pull the mass out because it is common here, here, and here. Notice that everything on the inside is a variable I do know. So I will be able to substitute numbers in there, but not for the mass. So I'm going to solve for this in terms of mass. Well, let's go over here where I substituted and solved. So here we go. I'm not going to take you through all the math, but basically I've substituted my numbers in, I've done the math, and what I end up with at the very end is a negative 97.125 M. So a couple things to note here. Notice the negative sign. That negative sign would indicate that we're losing energy from the system. So initially, the energy is bigger than the energy at the end. I'm losing energy. If this was a positive answer, what that would mean is basically I'm adding energy. So think about if this had some other force pushing it as it went down the hill, like I don't know, we put a rocket engine on the roller coaster or something that added energy to the system that wasn't initially there.